Hello everyone. I'm Naiqian Zheng from Peking University. Today, I'm glad to share our work, Automated Verification of an In-Production DNS Authoritative Engine. This is a joint work with Mengqi Liu, Linjian Song, Dong Li, Feng Han, Nan Wang, Yong Zhuo Liang, Zhai, and Ennan Zhai from Alibaba. Yuxing Xiang and my advisors, Xuanzhe Liu and Xinjin from Peking University. The full name of DNS is Domain Name System. The domain name system translates easy-to-remember domain names into IP addresses. It not only enables users to connect to the internet servers from their smartphones or the laptops, it is also widely used in the data centers for service indexing, load balancing, and etc. More specifically, DNS is classified into recursive server and authoritative server. The authoritative server is responsible to provide correct DNS responses, and the recursive server interacts with users and recursively queries the authoritative servers. The DNS functionality may be more complex than you think. Its specifications are composed of a couple of RFC standards, which includes wildcards, matching priorities, and complex rules parsing the domain tree. Some RFC standards are responsible for the tricky corner cases. So DNS responses have complex contents, including the status, flags, answer, authority, additional sections, and etc. Thus, common DNS softwares have complex implementations. The most popular DNS, Bind&I, has more than 50,000 lines of code, and our Alibaba Cloud DNS has more than 100,000 lines of code. Inside of the large code base, DNS has a lot of components for the front-end server, authentication, caching, and etc. Well, we all know that huge code bases are prone to bugs. DNS bugs have led to widespread network outages. The Facebook DNS, Cloudflare DNS, almost all widely used DNS systems have suffered from severe failures. This makes it necessary to improve the reliability of the DNS implementation. In October 2021, the social network Facebook became globally unavailable for 6 hours. And a few days later, .club DNS service responded with server failure messages. This failure caused a 3-hour outage for resolving .club domain all over the world. So what can we do to keep it reliable? One solution is testing, but it cannot provide very strong correctness guarantee. Another way is interactive verification. Prior work such as SAO4 and Certicals achieved significant success, but it usually requires person-years of manual proofs. We don't like this, we are lazy. And push-button verification leverages automated reasoning and symbolic execution to reduce human labors. But verifying that large code base is not feasible. Prior work, Groot, and a lot of existing work on network configuration verification focus on the correctness of the DNS configurations. Scale from NSDI leverages formal methods based on the DNS specification, but it did not try to verify the real code of the DNS system. In this paper, we focus on verifying the code, and more specifically, we focus on the authoritative engine. It is the most important component of the DNS because DNS messages are ultimately generated from the engine. All right, the question is how to verify an in-production authoritative engine. Our in-production DNS authoritative engine is of large scale. It has more than 2,000 lines of Go code and more than 50 functions. The path explosion and encoding strategy choosing challenge make it necessary to divide the entire program into layers and verify them one by one, which is called the refinement verification or layered verification. In the layered verification methodology, each layer is individually verified by its specifications, and the specifications serve as the dependency of other layers. Well, however, developing and maintaining specifications for each layer is very difficult for in-production software because the implementation is built by the developers without verification background. They usually prioritize rapid involving rather than formal methods. First, the program has unclean interface and improper function divisions. On the left is some layers of Certicals. Well, it's very good. It is an operating system designed for verification. Here you can see that each layer has clean functionality and clean interface. However, as for the in-production software, For example, the tree search module in our codebase has a lot of control flags and has different behaviors when used from different execution paths. The domain name decides whether it is inside the zone, and the flags decide the matching types such as wildcard, FQDN, NS, etc. This challenge occurs in many modules because DNS standards have many different match options and resource record types. So the verification requires specifications to describe what is correct, right? But in this case, it's very, very difficult to develop and maintain correct specifications for the layers. Even the DNS experts are not sure whether their specifications are already complete and correct. Second, the data structure encapsulation is not very friendly to verification. Most existing approaches require internal states to be maintained by the module's own functions. For example, good encapsulation should use, in this example, should use the isFull function, which is abstracted, to check whether the stack is full. Thus, the internal variable level disappears from the higher layer. But in production, higher level code usually relies on the concrete data types for interaction. In a bad encapsulation example, which is the bad level, which is in the code, is directly accessed by other modules. The bad encapsulation forces us to write more complex specifications to expose internal variables to outside. The code review of in-production software development usually do not focus on good encapsulation, so we cannot change them, we have to adapt for them. Third, the implementation of low-level functions is so complex that makes verification more difficult. For example, the developers usually use raw bytes and index offsets to present a domain name, rather than high-level string structure. It makes domain name compression full of complex control flow and massive memory load store operations. The developers intentionally choose to use raw bytes instead of high-level language for memory economy, but it raises difficulty on verification. Besides, in the production practice, the software is evolving rapidly to meet the changing requirements from the customers. So we have an additional requirement for verification, that is, it needs to be fast. To resolve these challenges, we proposed our automated verification tool, DNSV. It can verify an in-production DNS authoritative engine in a couple of person days. To resolve the unclean interface problem, we designed automated refinement with code summary technique to keep free from writing specifications for those for those modules. Basically, refinement verification takes specification and implementation as the input, runs symbolic execution, and based on SMD solver and outputs a yes or no. Because it's very hard to maintain the correct specification for each module, DNSV moves the specification to the output of the automated verifier. Here you can see, more specifically, it runs symbolic execution on a module and accumulates all past conditions together with the effects. After that, the verifier represents the module's behavior in an abstract form as a summary specification. Here is an example. The function is used for domain matching. Its input is the length of the domain name and labels for the domain name. The effects are returning a value and assigning a value for the pointer, node pointer. After summarization, the summary specification is like this. It has a lot of branches for the execution path, and the branch conditions are constraints on the input variables. And the effects are match result for returning value and match node pointer for assigning value for the input variable. We want to mention that finding a one-size-fits-all specification summary solution is very difficult, and we leverage the stateless property and limited effect pattern property of the DNS authoritative engine. Because of thanks to the stateless property, we can infer the inputs without internal memory states. And because of the limited effect patterns, we can infer the effects we can effect the effects with several limited patterns. The properties are based on the observation of our code base, and the techniques are domain-specific from the properties. For more discussion, please refer to our paper. For the poor data structure encapsulation problem, we choose to not abstract memory when direct access occurs. DNSV proposes a flexible memory model for partial abstraction. The flexible memory model allows both concrete code and abstract specifications to operate memory content. We model memory as a set of non-overlapping nested blocks, and each block contains an abstract array or struct whose contents can be either concrete or abstract. However, above two techniques are not enough to generate specifications for all modules. Some low-level modules are too complex for automated reasoning. Thus, manually designed abstractions are essential for addressing overly complex low-level lib functions. Fortunately, developing manual specifications is always almost one-time effort because the underlying lib functions rarely change. Developers with verification background analyze a module and create manual specifications. In the example of the domain name compression, the manual specification abstracts raw bytes into an array of integers based on the memory layout of the domain name. We also provide some domain-specific primitives, such as list equal for convenience. In addition, we want to talk about the methodology about where to use summary specification and manual specification. The summary specification have simple formulas and relatively large size encodings, so they are suitable for blue layers with complex input arguments and unclear functionalities. And the manual specifications are concise and highly abstracted, so they are suitable for yellow layers with complex internal logic but relatively clear functionalities. Like other verification framework, DNSV leverages layered refinement and requires humans to divide the program into layers. And the verification input of each layer is Go code, a configuration, and an optional specification. The verifier generates either a summarized specification or a verification result based on the manual specification. After that, the specification serves as the dependency of other modules, and the procedure will be repeated until the entire program is fully verified. More specifically, in each module, we translate Go code into LLVM IR and run simple execution to collect past conditions and effects. After that, we map them to abstract domain and generate summarized specification or produce a verification result for the given manual specification. DNSV is written in around 10,000 lines of Java code, and it relies on Go LLVM as a front-end to translate Go code into LLVM IR, as well as produce assertions on the unsafe behaviors. It uses Z3 SMP solver as symbolic execution backend. We have spent a lot of effort in the details, including how to support complex LLVM types and syntax, how to distinguish stub memory and heap memory, and how to encode a list with variable length. You can refer to our paper for more details. Next, we will share how we verify an in-production DNS authoritative engine with DNSV. The target code base is stateless and includes around 2,000 lines of Go code. We classify the modules into matching operations, lower layer library functions, in-heap memory, and runtime intrinsics. The blue modules are matching operations which are involving, so we use specification summarization on them. The orange modules are lower layer library functions which are relatively stable, so we write manual specifications for them. The green modules are LLVM intrinsics and Go runtime. They are inside the trusted computing base. And the green modules is the in-heap memory which holds the DNS records. We also add some annotations to assign concrete types for Go interface and separate the code from a very large Go code base. The top-level specification describes all related RFC standards and custom features used by the DNS engine. It is developed under the collaboration between developers with formal background and DNS background. We provide functional correctness and safety guarantee in the top-level specification. The functional specification decides the correct response for any query, and the safety guarantee ensures that it will not trigger any runtime error on any input. It is also worth mentioning that we rely on the control plane to supply a concrete in-heap domain tree as the runtime environment. The concrete domain tree removes unbounded loops and making the entire program behavior finite. It also avoids the reasoning of symbolic tree data structures simplifies the verification, especially for the specification summarization. To get the concrete domain trees, we generate thousands of zone files based on heuristics. Well, with the help of DNSV, we verified Alibaba Cloud DNS authoritative engine and prevented more than 10 deep and subtle issues. After that, DNSV kept up with the pace of bug fixing and software evolving. We found that some bugs cannot be fixed properly in one go, and sometimes fixing bugs even produce new bugs. Thus, the observation is that verification should be so fast that it can follow the pace of software evolving. Till now, DNSV has been deployed in Alibaba Cloud DNS system for half a year. And we are happy to see that with the help of DNSV, the average verification effort of each version is 1 person week. And optimally, we can verify a new version within 3 person days. The approach of DNSV is not tied to the specific code base we have verified. It can be generalized to other in-production systems with poor interface, poor encapsulation challenge, and with finite state, stateless property. Thus, we can apply the design principles and experiences to DNS recursive engines or other DNS implementations such as Band9, Core DNS, and they are the ongoing work. There will be also some opportunities to generalize DNSV to other network systems such as software-defined network, service mesh, and etc. All right. In this talk, we present DNSV, an automated verification tool for in-production DNS authoritative engine. DNSV leverages domain-specific techniques to resolve the in-production challenges. For the unclean function division, we use specification summarization, so the developers do not need to write a lot of specifications for layers with unclean division. And for the poor data encapsulation, we design a memory model to support memory access from both specification and code. And for the complex low-level specification, low-level function, we develop abstract manual specifications. Finally, with the help of DNSV, we are able to verify Alibaba Cloud DNS authoritative engine and continuously participate in its debugging and evolving. Thanks for your listening, and I'm very happy to answer any questions.
Yes, go ahead.
Hello, I'm Matthew Patchell from UNSW Sydney. Thanks for the talk, that was pretty neat. So you have to generate some concrete domain trees to get rid of unbounded loops. How confident are you that the trees that you generate actually cover everything you want to cover? And have you manually introduced bugs in your code base and made sure that they were caught by your testing framework?
Okay. We generate thousands of zone files based on heuristics of the scripts, and we have found some new works in the SIGOPS. They have more. They have better methodology to generate the zone files, and this is one of the limitations of our work, because we rely on concrete domain tree. So we cannot just enumerate all the input space because it is not finite. So what we can do is just to generate the trees as much as possible. And we have found that in the first 100 zones, we found a lot of bugs. And from the 100 to the 1,000, we found very few bugs. And after 1,000 complex zones, we cannot find any new bugs. And I think there may be some opportunities, for example, how to enable a just symbolic domain tree. And this might be the future work, I think.
This might be a bit more tricky, but yeah,
yes, thank you.
Thanks for that.
One more question?
Yes, thanks for the talk. Ralph Yong, ETH Zurich. I'm wondering, so you have a specification for your top-level specification, some kind of formalization of all these RFCs for what DNS is supposed to do. What have you done to validate that spec? Because as you said, it's lots of RFCs, they're complicated, they probably contradict each other. So like, what can be done there?
Yeah, that's a very good question. We struggled from the correctness of our specifications. And on the one hand, the specifications are developed by the experts, so they are relatively have more knowledge on the specification, on the RFC standards. And on the other hand, we have used some open source formal methods of the DNS specification, such as what we mentioned in the scale paper. And but these two are not enough to make it to ensure the specification is right. So frankly, the specification and the verifier is co-designed, and there is an additional question is how to make sure the verifier is correct. So in the development, we have a lot of false positive, and with the false positive, and we just to query the DNS experts to make sure whether the DNS to make sure whether the specification is right, or there's a bug in the verifier, or just this is a bug in the DNS implementation. So it is struggling, and it is really impressive. And I think it's very important to develop a very correct specification. All right, thanks.
Okay, thanks.
Okay, one last question.
Hello, Zheng from EPFL. Thanks a lot for the talk. Could you talk a little bit more about these automatically generated summarization specifications and what they are used for? I'm a little confused about whether they're meant to be consumed by humans or another part of the tool chain. Yeah.
In this slide, we talked about the methodology of choosing where to use the summarization specification and where the manual specification. As you can see, the yellow boxes they are relatively the lower layer lib functions, so they are very complex, and but the opportunity is that they usually stay stable. So we write manual specification for them, so we do not need to involve a lot. And for the blue modules, they are the matching operands, and they change every day, every month. So we use the specification summarization. And okay. And did I answer your question?
Yeah, I was just asking whether those specifications are validated by humans after being automatically generated, or are they plugged into the upper layer with some automated proof of refinement?
Yeah.
How do we know if they're correct?
Yes. These specifications are they are verified in the top layer, and we just trust them in the other layers, and until the top layer specification, which is manually developed to check whether the specification is right. And when we found there is a bug, there's something not the same with the specification and the real behavior. So we will check all the generated specifications, and this will help us to debug. Yeah, this is what we do.
Thank you.
All right, let's thank the speaker again.
Okay, thank you.